So far we've only used graphs and tables to evaluate limits, but here we're going to graduate from that. So we're going to do this now analytically without a graph or a table. The way we're going to figure out how this works is by looking at functions together with their graphs. So I have f of x here, and then the graph of f is over here. And we want to know right away the limit as x approaches 2. So we know for this one, we need to check two things. We need to check the limit as x approaches 2 from the left of f of x, and we need to check the limit as x approaches 2 from the right of f of x. Okay. And if they match, we have a limit. If they do not match, we do not. And that's reviewed from the previous lesson. Okay, so x approaching 2 from the right would be looking something like this, and x approaching 2 from the left would be looking something like that. So again, tells us which direction we're walking towards 2 from. And notice it does not matter, right? So either way, we end up at the same point. So these two values are both 4, which means my two-side limit is also 4. And this should not surprise us, right? Because we also know that if I just do plain old f of 2 rather, I get 4 because 2 squared, well, 2 squared is 4. And this should give us a hint on how to do it. So notice when I plug in that value, well, it's the same as my limit, right? These are equivalent. That always works for continuous functions. So if a function is continuous, we can just plug in that x value. So we had x equals 2. We could have just done 2 squared equals 4. And that's the same as the limit. The catch is that only works if a function is continuous. So maybe underline that in your notes. And this makes sense, right? If my function is continuous, well, I always end up at the same point regardless of the direction I'm walking, right? So it makes sense that I could just evaluate the limit very simply. Next, we're going to consider a piecewise function. And again, we're going to investigate the same way. I gave you the function f here, and over here on the right is my graph of f. Okay, so the reason we studied piecewise functions is mostly honestly because they're an easy way to learn how to do limits. And then the natural follow-up, right, is like, why are we doing limits then? They're not super useful in real life. They're not super interesting in and of themselves. You know, it's not super profound to say like this spot in this graph is in one spot and this spot is in the other. And the reason limits are a need to know is because they underlie a really important idea in calculus. If you take calculus with you next year, you will find that calculus is mostly about slope, and particularly about slope of curved functions. So we can already find slopes of lines pretty easily, but it gets harder when that slope is not constant. So maybe something like our parabola up here, right? So notice my slope is negative on this side and positive on this side. It changes depending on where the function is. Well, the way we find slope of a function like that is by taking 2 points on the function and making them closer and closer and closer together. And notice at that point where the 2 points meet up, that gives me the slope of an actual function. The way I represent that is by using a limit, taking a limit as delta x approaches 0, that change in x down on the bottom. So the reason why we study limits is that they allow us to study slope, which we know is useful, in a deeper way. So now as we look at our piecewise function here, notice I start at 1. Well, 1 is down here on this point of the graph. That's a continuous point. So this is going to be the same as just taking f of 1, right? I don't care that it's a piecewise function for that point because it's on a nice point of the graph. You know, obviously my left and right limits are going to be equal to each other. So I can just plug in 1, and that's going to be bigger than -4, right? And that's going to spit out, obviously, -5 from the graph, right? Now, all the rest of my values are going to take a little bit more checking, because notice they all have to do with the bound of the graph here. So we'll start with my positive side, my positive limit. Well, that's approaching from the right. And it looks like as those values get closer to -4 this way, my y values get closer to 5. So we don't care that it's an open circle there because we're talking about a limit. We're talking about which values the function approaches. And then from the left, well, when I approach from the left, I'm on this upper piece, and it looks like I'm approaching 6. So notice that tells us right away that this last limit, my two-sided limit, does not exist because, and we're going to write out our full justification, the left limit does not equal the right limit. Okay, so if I ask you to justify your answer, you don't have to write words necessarily. You can use your nice limit notation to show that. And it makes sense that that limit doesn't exist because, notice, that piece of the graph is discontinuous, right? Okay, so you already knew how to do all that. That was kind of a review. Evaluate limits with a graph. Now, let's talk about without the graph. So, for my right limit, well, my right limit is also going to be equal to what I get when I plug in -4 into the right-hand side of the function. Right? So notice if I do -3 minus 2 times -4, I get 5 as well. Right? And I chose that side because it's the greater than piece. Right? Same thing, if I use my less than piece to get the left limit, well, if I plug in -4 squared minus 10, I get 6. So really it's the same as we did before. You just have to plug in to the correct piece. So I can still find these just by plugging in. I just have to intentionally choose the correct piece of the function to plug into. And that piece depends on the direction the limit's asking for. And then here's the key point. So underline this a bunch of times in your notes. My two-sided limits only exist if both of my other two limits match. So for a two-sided limit, you check both.